We have previously studied the concepts of nuclear decay and half-life. Today we'll take a more quantitative look at these topics. First, let's take a look at the variables involved in nuclear decay problems. I'm going to use a popcorn analogy. When you're popping popcorn, you start with an initial number of unpopped kernels. The symbol N0 represents the number of parent nuclei. In our popcorn analogy, N0 would be the original number of unpopped kernels. As the popcorn kernels begin to pop, there are a decreasing number of unpopped kernels. These remaining unpopped kernels represent the number of parent nuclei remaining. They're represented by the variable n. Lambda is called the activity constant. It's the probability of decay occurring in the next time interval, usually 1 second, but the activity constant can have other units. It's important to note that lambda has nothing to do with wavelength of any sort in this equation. T is the elapsed time. It's how long since you started popping the popcorn, or in real life, it's how long we've been watching this sample of radioactive material decay. Capital A is the activity, which is the number of decays per unit time, usually decays per second. A decay per second is called a becquerel. The symbol is BQ. The rate of change of parent nuclei is equal to the decay constant multiplied by the number of remaining parent nuclei. It's negative because the number of parent nuclei is decreasing as time goes by. If we integrate this equation, we get a more useful equation. In this equation, we have N0, which again is the original number of parent nuclei, and multiplied by E, that's the natural number E, raised to the negative lambda t, where lambda again is the activity constant, usually in seconds to the negative 1, and t is the elapsed time since we've been watching the sample, usually measured in seconds. And of course, as we said earlier, n is the remaining number of parent nuclei. Since we will not usually know the actual number of parent nuclei, this rearranged form of the equation is even more useful. N divided by N0 can be represented as the fraction of the parent nuclei remaining. It's often represented as a percent. Let's look at the negative lambda t part of the equation. The units of lambda, the activity constant, and the units for t, the elapsed time, should be consistent such that when lambda and t are multiplied, the units will cancel. So for example, if t is going to be in seconds, then you need to be using the activity constant in seconds to the negative 1. If t is going to be in years, then you need to have an activity constant that is in years to the negative 1. We'll talk about that a bit more in the next slide. In case anyone has forgotten how to solve for lambda or t in this bottom equation, keep in mind that what we're looking at here is an exponential function. So if we take the natural logarithm of both sides of this equation, we end up with this relationship. The natural log of n divided by n0 is equal to negative lambda t. Don't forget the negative sign. Since it's not easy to measure lambda directly, lambda, the activity constant, is usually calculated from the half-life t sub 1/2. The activity constant lambda is the natural logarithm of 2 divided by the half-life. When you use your calculator for this, you want to be sure you're using the ln button for natural logarithms and not the log button, which is for common or base 10 logarithms. If the half-life is measured in seconds, then lambda will be in seconds to the negative 1, and t in the equation on the previous slide must be in seconds. If the half-life is in years, then the activity constant will be in years to the negative 1, and the elapsed time t in the equation must be in years. As long as the units of time are used consistently between the half-life, the activity constant, and the elapsed time, then you can use any convenient units of time. Sometimes we want to predict the activity in decays per second of a sample of a radioactive substance. This equation will allow you to calculate the activity in decays per second, or becquerels, of a sample. if you know the original number of parent nuclei, the activity constant, and the amount of time that has elapsed. That's all for now, except I do have a wacky word definition for you. Today's word is polarize. Polarize, what penguins see through.